While not strictly a navigation system, the horizontal situation indicator, also referred to as the HSI, is unique in the way it displays navigation data from various navigation sensors such as VORs, NDB, GPS, and others. The HSI is actually two instruments in one. A heading indicator, as you can see from the compass rose display, and a VOR indicator. The aircraft depiction is in the center. To fly the HSI, you turn the HSI selector knob until the top of the needle indicates your desired heading. If you turn to that same heading, then the CDI indicates the course you seek is to your left or to your right, and you can turn towards the desired course to intercept it at an angle. The tail of the CDI needle here represents the reciprocal of the heading selected with the CDI pointer. The best part of the HSI is the center visual depiction of a small aircraft and the angle of intercept that it shows for the selected radial. This gives you a great visual representation of your situation. The HSI also has a to/from indicator and a glide slope indicator. This indicator drops or rises into the instrument face when properly tuned when flying an instrument approach using a glide slope. When the glide slope needle is centered, you are flying on the glide slope at that moment. With all of this visual information on one instrument, it's easy to see why it's called horizontal situation indicator. Now, another advantage of an HSI over a conventional heading indicator and VOR is that most are magnetically slaved. This means the HSI automatically seeks and holds magnetic north and does not need continual precession checks from the pilot. This slaving is accomplished through a remote magnetic sensor called a flux detector. It's typically located out on a wing and senses the Earth's magnetic field and automatically corrects the HSI. The HSI system also allows for slaving control. This lets the pilot manually correct a large amount of deviation on the HSI display. The deviation meter on the slaving control indicates the amount of correction applied to the HSI. Now let's use the HSI in flight to capture the 265-degree radial, for example. The top of the HSI compass rose shows our heading. After we've identified and tuned in the VOR station we want to use, we adjust the course deviation indicator until the head of the needle points to the selected course that we want to track to the station. The tail of the needle points to the reciprocal. This is the same as the radial as it radiates from the station. So now our radio and HSI are correctly tuned and set. By looking at the center of the HSI instrument display, we see a depiction telling us the relationship between the aircraft heading and the radial. If the CDI is deflected to the left or right of the head pointer, then that shows how to intercept the indicated radial. Usually you want to make this intercept angle at about 30 to 40 degrees, in this case 340 degrees. As the aircraft begins capturing the 340-degree radial center line, the deflected CDI begins to move towards the center, aligning with the head and tail of the needle. As this movement occurs, begin turning the aircraft towards the center line at a turn rate matching the needle's rate of movement so that the aircraft and the needle agree with each other on the 265-degree radial. It's a very satisfying feeling to roll out on the course center line at the same time the CDI needle centers. Note that you will have reverse sensing if you're flying the back course. You know you're on the back course if the HSI is set to the reciprocal of where the localizer is positioned. For example, if the HSI is tuned to 090 but the localizer is on the 270 extension, then you're on the back course and you'll have reverse sensing. We'll cover this more in greater detail later on.